Okay, so today we are going to start chapter 3, which is the logic of quantified statements. The opening definition for the chapter is a predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for the variables. The domain of a predicate variable is the set of all values that may be substituted in place of the variable. Let's see here. Finding the truth values of a predicate. Take P of x. Is the predicate x squared is greater than x? Okay. With the domain of domain is real numbers. Which of the following are true? Is P of 2 true? P of 2. If P of x is the x squared is greater than x, yeah, it is true. What about P of 1/2? No. So it's not in the truth set. P of negative 1/2? Negative 1/2? Think about it. Negative 1/2 is negative 1/2 squared greater than negative 1/2? Yes, it is. Because it's positive 1/4. So another definition for you. If P of x is a predicate and x has domain D, the truth set of P of x is the set of all elements of D that make P of x true when they are substituted for x. The truth set of P of x is denoted by this. Okay, the truth set is x element of D such that P of x. This chapter gets more heavily into the using of symbols and stuff like that than rather than words, like more like a true math class in that regard. So, looking at this here, the truth set here would be set of all x, or x element of R, such that P of x. Okay? Take the, how about Q of n is the predicate, n is a factor of 8. Let's see, Q of n is a factor of 8. What is the truth set of Q of n if the domain is Z? Domain is the set of integers. What is the truth set for Q of n? If you would denote it with n element of z such that n is a factor of 8. What is the truth set?
1, 2, and 4.
And be complete. It's not just positive integers.
Negative 2.
Mm-hmm.
Negative 1. Negative 4.
And
Negative 8.
exactly. There you go. So minus 8, minus 4, minus 2, minus 1, 1, 2, 4, and 8. This is another way of building sets by giving rules and an initial domain. So like I said, another way of defining a set. Okay, let's see here. The universal quantifier. You can make a predicate a statement by assigning values to all the variables. This was done in the previous example. Another way to do this is to use quantifiers. Quantifiers are words that refer to quantities such as some or all and tell for how many elements a given predicate is true. A, in the inverted A, is the universal quantifier. It can be read as for every, or for each, or given any, or for all. So the sentence, every human being is mortal, can be expressed as for all humans, X is mortal. Of course, you could also put it as a for all X element of humans, X is mortal. Another definition for you. Let Q of X be a predicate and the domain and D the domain of X. A universal statement is a statement of the form like here, for all of X element of D, Q of X. It is defined to be true if and only if Q of x is true for each individual x in D. It is defined to be false if and only if Q of x is false for at least one element x in D. The value for x for which Q of x is false is called a counterexample to the universal statement. So, consider Q of x is x squared is greater than x. Greater than or equal to x. D is 1, 2, 3, 4, 5. And you want to say whether or not for all of x element of D, Q of x. Is that true or false?
False.
Is it? X squared is greater than or equal to x? It's true. You could demonstrate its truth by plugging each element of D into the equation and seeing if it is true for each element in the domain. Now consider if you changed it to is that true? If you change the domain to real numbers. No. X squared is not greater than or equal to x if x is 1/2. That's a counterexample. All you need is 1 to show that this is false. So you have the counterexample of 1/2. So now if the domain were z, all integers, then it would be true. Because 0 squared is 0, 1 squared is 1, minus 1 squared is 1, which is greater than x. So that is the universal quantifier. Now the counter to that is the existential quantifier. It is denoted by the inverted E. The existential quantifier denotes there exists for some for example, there is a student in Math 140. There exists a person that is a student, that such that the student is a student in Math 140. So, say there exists a P such that P is a student. P is a student in Math 140. So all you need is one to demonstrate this truth of the statement. There exists for some, not for all, but for some P, which is a person, which is an element of all people, where P is a student in Math, such that P is a student in Math 140. For example, another example, there exists M, element of Z, Z plus, such that M squared equals M. Rather than having to prove it all for all the, say it's true for all the elements of Z plus positive integers, you only have to demonstrate that it's true for one. So is the statement true? Yeah. By example, M equaling 1. Now let E say E equals 5, 6, 7, 8. How about all elements M, element of E, such that M squared equals M? To show it's true or false, to show it's true, all you need is one example. To show it's false, you need to demonstrate all elements of the domain make the predicate false. So is that true or false? False, because 5 times 5 is 25, 36, 49, 64 are your squares, and they're not all, and none of those are elements of E. So why this section was injected in this at this particular point, I'm not sure, but this is a formal language, using very symbols, unequivocal statements, that sort of thing. So you need to be able to go from formal to informal language and back again. It is important to be able to go between the two when dealing with mathematical problems. So what are some informal ways to express all x r? How would you informally put that statement? That's a formal statement. How would you say that?
For all, there is a real number.
No, that's a universal quantifier, not the existential.
It's for all informal, or
Yeah, for all, that's informal. Yeah.
for all real numbers, where is greater than 0 or equal to.
Sounds good. Yeah. So how about for all x element of R, x squared does not equal -1. Somebody else. How would you put that informally? Regular words. Anybody? There you go. That is a way to put it. Yes. What about saying the following statement so that the quantifier trails the rest of the sentence? For any integer n, two n is even. I think that's what I had. Yeah. Put the quantifier at the end. Where's the quantifier? What words indicate a quantifier? Exactly, for any. So put the quantifier at the end. You would say for any integer. The twice any integer is even. You know, there's lots of ways to say it informally, but formally, you would say for all it's very clear what that means, and it could be read in different ways. For any integer n, 2n is even. For any integer, twice the integer is even. Twice any number, twice a number is even for any integer given. Lots of ways to say it informally. Mathematically, you put it in and use symbols and use variables to make it clear and formal. so you can manipulate it and draw conclusions and that sort of thing. What about the following statements with using quantifiers and variables? Let's say all triangles have 3 sides. How would you put that formally? For all t elements of triangles, the set of triangles, t has 3 sides. Now, here's something a little bit different. How could you express that? Oh, the tilde thing? The squirrely? The wavy line? That's one way to do it, yes. So there doesn't, and you'd use the existential quantifier, there doesn't exist D element of dogs such that D has wings. Unless they drink Red Bull. Anyway, but that's one way of doing it. Or you can say, for all D element of dogs, D does not have wings. Which kind of gets us a little ahead of things when we get into this is the negation of this, and vice versa. 2 ways of expressing formally the same thing, depending on how you want to do it. So how to convert from a negation to a non-negation will be covered a little bit later. So then we can get into universal conditional statements. Yeah, this is informal to formal, and this was formal to informal we discussed on the previous page. So universal conditional statements. Okay. They take the form of for all x element of D, if P of x, then Q of x. Or you could use the arrow instead of the if and then, because it is a conditional. So let's see here. Example here. For all x element of R, if x is greater than 2, then x squared is greater than 4. Yeah. If you can read that informally, what would that be? If for all real numbers greater than 2, that number squared is greater than 4. You typically don't use variables in informal wording, whereas the formal is more yeah. Yeah. Equivalent forms of universal and existential statements. Let's see here. Let's see here. Equivalent forms. Okay. So take the two statements. For all real numbers x, if x is an integer, then x is rational. And for all integers x, x is rational. Pretty much the same thing, right? Kind of. Gets the same point across. So say P is P of x. X is an integer. Q of x is rational. So you can say for all x elements of real numbers, if p of x then q of x. Right? But since this defines a set here, it can also be written as for all of x, element of z, x is an element of q. In short, let's see here, where D is a subset of U consisting of all values of the variable x that make P of x true. So you have two sets. The set that makes this true, so if Z is a subset of R, so the set of P that satisfies the P is a subset of the set of R of the domain here. You can use that subset and eliminate the P predicate. And I should have put a different letter for Q because that's let's see here. X is an element of rational numbers. So but let's see here. Two statements. Let's see here. All squares are rectangles. Informally. For all S element of R rectangles, or element of rectangles, if S is a square, for all shapes, as elements of let me get that. Then S is a rectangle. Let me put shape here. If S is a square, then S is a rectangle. Okay. Can also be written as for all S element of squares, S is a rectangle. Because squares are a subset of shapes. Let's see here. There exists let's see here. The P of n, P of n, and is prime. E of n is even. There exists an n element of real numbers such that P of n and E of n or you could say there exists an element of primes such that E of n. By looking at the subset, because primes are a subset of R. Let's see here. Bound variables and scope. Now this sounds like something out of a programming class. Have you all got into programming where you talk about the scope of variables? No? You're in 119? You're in 119? I think they cover that in 119. But where a variable is valid. Consider the following two statements. For every integer x, x squared is greater than or equal to 0. And then there exists a real number x such that x cubed equals 8. So they both use the variable x, but they have different scope. Both statements use the variable x, and we say that the variable x is bound by the quantifier that controls it, and that its scope begins when the quantifier introduces it and ends at the end of the quantified statement. So in this case, n is only in this case they refer to the same thing, but n could be referring to two different things in the two statements, because n is valid in this scope here, and this n is valid in this scope here. Outside of those statements, n has no meaning. It is defined by and bound by the quantifier that introduces the statement. Let's see here. I'm going to do one more section here. Implicit quantification. If a number is an integer, then it is a rational number. Universal statement without the telltale word all or every or any or each. The indefinite article a is the only indicator. A little notation here. If P and Q are predicates, and suppose the common domain of X is D, so P of X and Q of X is an element of D, some domain. The notation P of X double kind of a double arrow there, Q of X that indicates that every element in the truth set of P is in the truth set of Q, or equivalently, for all X element of D, P of X, and it implies Q of X. The notation P of X with a double direction arrow that indicates that P of X and Q of X have identical truth sets, or equivalently, for all X element of D, P of X, if and only if Q of X. The truth set is a subset of Q of X, and truth set of P of X is the same as Q of X. Yeah. So P of X has a truth set that's a subset of Q of X, a subset of the truth set of Q of X. Here, and with this symbol, they are the same. So there is that notation. Now, the slides at the end of this section, I don't know if are we in section 2 here? Are you following along with the slides? Section 2 of chapter 1 or section 1 of chapter 1? Or chapter 3, sorry.
This is all in one slide first.
Oh, 3.1? Okay, it's all 3.1. Okay, at the end of this section, there's the slides introduce a game or a program developed to teach principles of logic. It's called Tarski's World. Going through those on the slides involves jumping back and forth between multiple slides and all that sort of stuff. So I don't cover it in class, but I leave it to you guys to look at the slides at the end of chapter 3, section 1, and learn about Tarski's World. So there you go. We'll get into the negations of quantified statements on Thursday. In the meantime, have a good day and see you in a couple of days.